James Webb found a planet better than Earth, the discovery that changes everything. On a routine observation night in September 2024, astronomer Dr. Sarah Chen was reviewing spectroscopic data from the James Webb Space Telescope when she noticed something that made her hands freeze over her keyboard. The atmospheric signature she was seeing from exoplanet K2-18b shouldn't exist. The molecular fingerprints, water vapor, carbon dioxide, methane, and something else, something impossible, were telling her that 124 light-years away, orbiting a cool red dwarf star, they might be a world not just capable of supporting life, but actually superior to Earth in almost every measurable way. What she discovered over the following months would ignite the most intense scientific debate of the century and force humanity to confront an uncomfortable question. What if Earth isn't the best planet for life in the universe? What if we've been living on a cosmic backup world while paradise exists elsewhere? The evidence is mounting, and it's more compelling than anyone wants to admit. K2-18b wasn't supposed to be anything special. Discovered in 2015 by NASA's Kepler Space Telescope, it was catalogued as just another exoplanet, one of thousands found that decade. The discovery itself was unremarkable by astronomical standards. The planet revealed itself through the transit method, causing a tiny periodic dimming of its parent star's light as it passed in front of the stellar disk every 33 days. The planet orbits K2-18, a red dwarf star in the constellation Leo, about 124 light-years from Earth. In cosmic terms, that's practically our backyard, a distance that light covers in just over a century. The star itself is unremarkable, an M-dwarf about 1/3 the mass of our Sun, cooler and dimmer, but with a lifespan measured in trillions of years, rather than our Sun's mere 10 billion. K2-18b is roughly 2.6 times Earth's radius and about 8.6 times Earth's mass. These dimensions place it squarely in a category astronomers call mini-Neptunes or sub-Neptunes, worlds larger than Earth but smaller than Neptune. For years this classification carried an implicit assumption. Such worlds would be like scaled-down versions of Neptune, with thick hydrogen atmospheres, no solid surface, and conditions completely hostile to life as we know it. The planet completes one orbit every 33 Earth days, placing it at a distance of approximately 0.1429 astronomical units from its star, about 13.3 million miles, compared to Earth's 93 million miles from the Sun. This might seem dangerously close, but K2-18 is so much cooler and dimmer than our Sun that this orbital distance places K2-18b squarely within the star's habitable zone, that Goldilocks region where temperatures theoretically allow liquid water to exist. But here's what made K2-18b easy to overlook for nearly a decade after its discovery. It didn't fit the profile of what astronomers were desperately searching for. The exoplanet community had become laser-focused on finding Earth 2.0, rocky planets nearly identical to Earth in size, orbiting Sun-like stars at Earth-like distances. K2-18b was too big, orbited the wrong type of star, and belonged to a planet category assumed to be uninhabitable. That assumption was about to be shattered in the most spectacular way possible. Dr. Sarah Chen had been an astronomer for 15 years, specializing in exoplanet atmospheres. She'd analyzed hundreds of spectroscopic datasets, looking for the chemical fingerprints of distant worlds. Most nights were routine, collecting data, running it through analysis pipelines, cataloging results. September 11, 2024 started no differently. James Webb had been allocated observation time on K2-18b as part of a larger survey of sub-Neptune exoplanets. The goal was straightforward: characterize their atmospheric compositions to understand what these intermediate-sized worlds were really like. Were they small gas giants? Rocky planets with massive atmospheres? Something else entirely? When K2-18b passed in front of its star, Webb's instruments captured starlight that had filtered through the planet's atmosphere. Different molecules absorb light at specific wavelengths, creating absorption lines in the spectrum, like a chemical barcode. By analyzing these lines, astronomers can determine what gases are present in the atmosphere, even from 124 light-years away. Dr. Chen pulled up the process spectrum on her screen at 11:47 p.m. The first features that jumped out were expected. Water vapor absorption bands in the infrared. That was encouraging, but not shocking. Water vapor had been tentatively detected in K2-18b's atmosphere by Hubble in 2019, though those observations were at the edge of detectability and remained controversial. Then she saw the carbon dioxide signature, strong and unambiguous. That was more interesting. It suggested the planet had geological or atmospheric processes cycling carbon, or possibly even a carbon-based life chemistry. The methane bands appeared next. Her pulse quickened. Methane in the presence of water vapor and CO2 created an intriguing chemical puzzle. On a lifeless world, methane should react with other atmospheric components and disappear relatively quickly. Its persistence suggested either continuous geological production or something else. Then, at precisely 11:52 p.m., Dr. Chen noticed an absorption feature at 3.3 micrometers that didn't match anything in her reference database of common atmospheric molecules. She ran the spectrum through 3 different analysis programs. All gave the same answer: dimethyl sulfide. Her coffee mug hit the floor, shattering. She didn't notice. Dimethyl sulfide, chemical formula CH32S, is a compound with one overwhelmingly important characteristic. On Earth, it's produced almost exclusively by biological processes. Ocean phytoplankton synthesize it as a metabolic byproduct. It's one of the molecules responsible for the characteristic smell of the sea. In Earth's atmosphere, it plays a crucial role in cloud formation, with the sulfur particles serving as condensation nuclei. Most importantly, no known abiotic process, no geological activity, no photochemistry, no atmospheric physics produces dimethyl sulfide in significant, detectable quantities. It's what astrobiologists call a biosignature, a molecule that strongly suggests the presence of life. Dr. Chen's hands were shaking as she reached for her phone. She called Dr. Niku Madhusudan at Cambridge University, the principal investigator for the observation program. It was 4:52 a.m. in Cambridge. "This better be important, Sarah," Madhusudan answered groggily. "Niku, you need to get to your computer right now. I'm seeing DMS in K2-18b's spectrum." There was a long pause. "You're certain?" "The signal-to-noise ratio is 4.8 sigma. The absorption feature is exactly where it should be for dimethyl sulfide. I've checked it 6 times. Another pause. "I'm getting up. Send me everything. And Sarah, don't tell anyone about this yet. If this is real, we need to be absolutely certain before it gets out." The verification process. What followed was 3 months of the most intensive scientific verification process Dr. Chen had ever experienced. The team couldn't simply announce the detection. The implications were too profound, the potential for error too embarrassing, and the scrutiny from the scientific community would be merciless. The first question they tackled: could the DMS signal be a false positive? Perhaps it was actually a different molecule with a similar absorption feature, or multiple molecules creating an overlapping signature that mimicked DMS. They tested every alternative hypothesis they could imagine. Sulfur dioxide? No. SO2's absorption features were in the wrong locations and the wrong relative strengths. Hydrogen sulfide? Wrong molecular geometry, wrong spectrum. Carbon disulfide? Closer, but still didn't match. Methanethiol? Similar to DMS, but with distinct differences in the spectrum that weren't present in their data. They ran the spectrum through every molecular database available, checking against thousands of known compounds. Nothing fit except dimethyl sulfide. Next, they examined possible instrumental artifacts. Could Webb's instruments be creating a false signal? They compared their observations to calibration data, checked for systematic errors, and analyzed observations of other planets taken around the same time. No anomalies appeared. The signal was real, not instrumental. Then came the hardest question. Could any non-biological process produce DMS on K2-18b? Dr. Madhusudan assembled a team of geochemists, atmospheric chemists, and planetary scientists. They built computational models of K2-18b's atmosphere and ran thousands of simulations, testing every conceivable abiotic mechanism. Volcanic outgassing. On Earth, volcanoes release sulfur compounds but not DMS. Could K2-18b's geology be different? They modelled various volcanic chemistries, including sulfur-rich magmas under different pressure and temperature conditions. None produced significant DMS. Photochemistry. Could ultraviolet light from K2-18 drive chemical reactions that synthesize DMS from simpler molecules? They built detailed photochemical models incorporating K2-18's spectrum, which is weighted toward infrared rather than UV. The models showed that DMS, if formed through any conceivable photochemical pathway, would be destroyed faster than it could accumulate. To maintain the observed levels, something would need to be continuously producing it. Surface chemistry. Perhaps reactions between the ocean and the atmosphere, or between different atmospheric layers, could generate DMS. They tested models involving various ocean chemistries, from pure water to exotic brines, under different temperature and pressure regimes. No plausible mechanism emerged. Meteoritic input. Could DMS be delivered by impacts from comets or asteroids? The required impact rate to maintain observed DMS levels would be so high that K2-18b's atmosphere should show other evidence of constant bombardment. It didn't. After exhausting every alternative, the team reached an uncomfortable conclusion. If the DMS detection was real, the most parsimonious explanation was biological production. But they still needed to verify the detection itself. Were they really seeing DMS? Or was this an artifact of their data processing? The second observation. In January 2025, James Webb observed K2-18b again during another transit. This second observation would either confirm or refute the September detection. If DMS was really present, it should appear again. If the original detection was a fluke, random noise that happened to look like DMS, the second observation would show something different. Dr. Chen watched the data come in with an anxiety she'd never experienced before. Her entire career, perhaps the most significant scientific discovery in human history, hung on what these photons from 124 light-years away would reveal. The spectrum appeared on her screen. She analysed it with practiced efficiency, though her heart was pounding. Water vapour, present. Carbon dioxide, present. Methane, present. At 3.3 micrometers, a clear absorption feature. Dimethyl sulfide. The signal was even stronger in the second observation, 5.2 sigma significance. Not only was DMS present, but the concentration had apparently increased slightly between September and January. This temporal variation was itself significant. It suggested dynamic processes, not just a static atmospheric composition. Dr. Madhusudan's paper, submitted to Nature in March 2025, was cautiously worded. We report the detection of dimethyl sulfide in the atmosphere of the sub-Neptune exoplanet K2-18b. While biological production represents the most straightforward explanation for this biosignature gas, we cannot definitively rule out all abiotic mechanisms. Additional observations and theoretical work are needed to confirm the biological hypothesis. The paper included an exhaustive analysis of alternative explanations, detailed error analysis, and frank discussion of the detection's limitations. The team bent over backward to be conservative. It didn't matter. When the paper was released in May 2025, the world exploded. The media storm and scientific debate headlines around the globe proclaimed, "Alien life discovered on nearby planet," and "James Webb finds living world." The more responsible outlets hedged, "Possible biosignature detected on exoplanet," and "Signs of life on K2-18b." The scientific community's reaction was intense and divided. Some researchers hailed the discovery as the most significant in human history. Others urged extreme caution, pointing out that claiming extraterrestrial life based on a single molecular detection would be premature and potentially embarrassing if later refuted. Dr. Victoria Meadows at the University of Washington, a leading expert on biosignatures, articulated the skeptical position. DMS is an intriguing detection, but we've been fooled before. Remember the phosphine on Venus? That detection got everyone excited about possible life in Venus's clouds, but subsequent observations and reanalysis showed the signal was likely sulfur dioxide, not phosphine. We need to be very, very careful before claiming we've found life on K2-18b. She had a point. The 2020 phosphine announcement for Venus had followed a similar pattern. A molecule associated with life on Earth, detected in an exoplanet atmosphere, extensive media coverage, then months of debate followed by the likely conclusion that the detection was wrong or misinterpreted. But Dr. Madhusudan's team had learned from that episode. Their analysis was more rigorous, their signals stronger, their alternative explanations more thoroughly explored. They'd done everything right. Still, the scientific method demands skepticism. Extraordinary claims require extraordinary evidence, and claiming extraterrestrial life is perhaps the most extraordinary claim possible. The debate raged through academic conferences, scientific journals, and Twitter threads. Some astronomers began planning additional observations with different instruments to confirm the detection. Others worked on theoretical models to find any overlooked abiotic mechanism that could explain DMS. Dr. Sarah Seeger at MIT proposed an alternative. What if K2-18b has some exotic chemistry we've never considered? Perhaps under the high-pressure conditions of a hydrogen-rich atmosphere, there are catalytic reactions we don't know about that can synthesize DMS from simpler precursors. We can't claim life until we've exhausted every conceivable, non-biological explanation. It was a fair critique, but it also highlighted an uncomfortable truth. You can never truly exhaust all possible alternatives. There will always be some hypothetical scenario, however unlikely, that could explain an observation without invoking life. At some point, you have to make a judgment call about what's most probable. Meanwhile, another aspect of K2-18b was getting attention from a different group of researchers. Planetary scientists studying the physical characteristics of sub-Neptune worlds. They were realizing that K2-18b wasn't just potentially inhabited. In many ways, it might be a better home for life than Earth itself. The Hycean world hypothesis. To understand why K2-18b might be superior to Earth, you need to understand a revolutionary new concept in planetary science: Hycean worlds. The term Hycean was coined in 2021 by Dr. Niku Madhusudan's group at Cambridge, combining hydrogen and ocean. These are worlds with massive, hydrogen-rich atmospheres overlying deep, planet-wide oceans. K2-18b appears to be the first confirmed Hycean world studied in detail, and understanding this new category of planet requires rethinking everything we thought we knew about habitability. For decades, the search for habitable worlds focused almost exclusively on finding Earth twins, rocky planets similar in size and mass to Earth, orbiting sun-like stars at Earth-like distances, with nitrogen-oxygen atmospheres. This approach made intuitive sense. We know Earth works for life, so finding Earth's duplicate seemed like the most promising path to discovering life elsewhere. But this Earth-centric thinking was limiting in ways scientists are only now recognizing. The universe might have multiple solutions to the habitability equation, and some of those solutions might be more common and more stable than Earth's configuration. Hycean worlds represent a fundamentally different architecture for habitability. Their key characteristics: massive hydrogen atmospheres. Unlike Earth's thin nitrogen-oxygen envelope, Hycean worlds have thick atmospheres dominated by molecular hydrogen, H2. This sounds hostile. Hydrogen is explosive and seemingly incompatible with life, but that's only true in the presence of oxygen. In a hydrogen-dominated atmosphere with minimal free oxygen, hydrogen is inert and stable. These atmospheres are so thick they create enormous greenhouse warming, keeping the planet's surface warm enough for liquid water, even at orbital distances where Earth would freeze. Global oceans hundreds of kilometers deep. Earth's oceans average 3.7 kilometers deep. Hycean worlds likely have oceans orders of magnitude deeper, potentially 100 to 500 kilometers. This provides an enormous volume for aquatic life to develop, evolve, and diversify. The pressure at these depths is crushing by Earth standards, but life is remarkably adaptable to pressure. Earth's deepest trenches at 11 kilometers depth host complex ecosystems. No exposed land. Hycean worlds are predicted to be entirely ocean-covered, with no continents or islands. This might seem like a disadvantage, but consider, on Earth, most mass extinctions correlate with volcanic eruptions, asteroid impacts on land, or rapid climate changes driven by continental configuration. A world with no land has no continental volcanism, no mountain ranges affecting atmospheric circulation, and potentially more stable climate. Moderate surface temperatures. Despite orbiting close to their stars, Hycean worlds maintain moderate surface temperatures through a delicate balance. The thick atmosphere provides greenhouse warming, but cloud cover and the ocean's enormous thermal inertia prevent runaway heating. surface temperatures likely range from just above freezing to perhaps 50 degrees Celsius, 122 degrees Fahrenheit. Warm, but not prohibitively so for life. Long-term stability. Red dwarf stars like K2-18 are the most stable and long-lived stars in the universe. Once they settle into their main sequence phase, they can shine steadily for trillions of years, 1,000 times longer than Sun-like stars. A Hycean world orbiting a red dwarf could remain habitable for timescales that dwarf Earth's entire existence. Dr. Madhusudan explained the revolutionary implications. For decades, we've been searching for Earth 2.0, assuming that Earth's particular configuration is the only viable path to habitability. But K2-18b is showing us that nature found a completely different solution, and it might be a better solution in many ways. Hycean worlds could be the universe's preferred architecture for hosting life. Why K2-18b might actually be better than Earth. Let's conduct a direct comparison between K2-18b and Earth across the factors that determine a planet's ability to host, sustain, and nurture life. In several crucial categories, K2-18b appears to have significant advantages. Climate stability. K2-18b wins decisively. Earth's climate is surprisingly volatile. Over the past 500 million years, our planet has experienced numerous ice ages, hothouse periods, and dramatic climate swings. The Paleocene-Eocene thermal maximum, 56 million years ago, saw temperatures spike by 5 to 8 degrees Celsius globally within a few thousand years. The snowball Earth episodes, between 720 and 635 million years ago, saw the entire planet freeze over, with ice extending to the equator. These climate fluctuations drove mass extinctions and forced life to repeatedly adapt or perish. While this evolutionary pressure might have spurred innovation and complexity, it also meant that countless lineages went extinct because they couldn't adapt fast enough. The causes of Earth's climate instability are numerous. Orbital variations. Earth's orbit around the Sun isn't perfectly stable. Over tens of thousands of years, the orbital eccentricity, axial tilt, and precession vary, Milankovitch cycles, causing climate fluctuations that trigger ice ages. Continental drift. The slow movement of continents changes ocean circulation patterns, atmospheric flow, and the distribution of land at different latitudes, all affecting global climate. Volcanic activity. Large eruptions can cool the planet by throwing sulfur into the stratosphere, while extended volcanic episodes can warm it by releasing greenhouse gases. Asteroid impacts. Large impacts throw dust into the atmosphere, causing rapid cooling and potentially triggering extinctions. Solar variability. Though our Sun is relatively stable, its output varies slightly over decades to millennia, affecting Earth's climate. Feedback loops. Earth has numerous climate feedback mechanisms: ice albedo feedback, methane clathrate release, carbon cycle perturbations, that can amplify small changes into large ones. K2-18b appears immune to most of these instabilities. Tidal locking provides stability. K2-18b is likely tidally locked to its star, meaning the same hemisphere always faces the star. While this creates a day-night temperature gradient, the massive ocean and thick atmosphere efficiently transport heat from the day side to the night side. This heat transport is self-regulating. If the day side gets hotter, the increased temperature gradient drives stronger circulation, moving heat to the night side faster. Computer models show that tidally locked Hycean worlds can maintain remarkably stable global temperatures. No continental drift. With no continents to rearrange themselves, ocean circulation patterns on K2-18b should remain constant over billions of years. The absence of continental configuration changes eliminates a major source of long-term climate variation. Massive thermal inertia. A water layer hundreds of kilometers deep has enormous heat capacity. The ocean would absorb and release heat on timescales of thousands to millions of years, buffering against any short-term perturbations. To put this in perspective, Earth's oceans, which average less than 4 kilometers deep, contain enough heat to delay climate change responses by decades. K2-18b's ocean, perhaps 100 times deeper, would have thermal inertia 100 times greater. This is climate stability on a level Earth cannot match. Thick atmospheric buffer. The dense hydrogen atmosphere would absorb and redistribute heat efficiently. It would also provide protection against external perturbations. A massive asteroid impact or volcanic eruption would have its climate effects diluted across an atmosphere perhaps 100 times more massive than Earth's. The climate disturbance would be proportionally smaller and shorter-lived. Stellar stability. K2-18, being a mature red dwarf, is extraordinarily stable. Red dwarfs can flare violently when young, but once they settle down, which K2-18 did billions of years ago, they maintain nearly constant output for trillions of years. Earth's sun, in contrast, has brightened by about 30% since the solar system formed, and will continue brightening until it eventually expands into a red giant and destroys Earth. K2-18b's star presents no such threat on any conceivable timescale. The climate stability implications are profound. Life on K2-18b wouldn't face the repeated near extinctions that Earth life has endured. Evolution could proceed more gradually, with less premium on adaptability and more opportunity for specialization and complexity. Long-term evolutionary trends could develop without periodic disruptions. Available energy. Earth holds a slight edge. Life needs energy. On Earth, nearly all energy for life ultimately comes from the sun through photosynthesis. Plants, algae, and photosynthetic bacteria capture sunlight and convert it into chemical energy, sugars, which then flows through food chains. Even most deep-sea ecosystems ultimately depend on organic matter sinking from sunlit surface waters. Earth's sun is an ideal energy source, a yellow G-type star emitting copious energy across the visible spectrum, with peak output at wavelengths where chlorophyll efficiently absorbs. This has allowed Earth's biosphere to flourish, producing vast amounts of biomass, an estimated 550 gigatons of carbon in living organisms. K2-18b's situation is more complex. Lower total energy. K2-18, being a red dwarf, produces less total energy than the Sun. Even though K2-18b orbits closer to its star than Earth does to the Sun, it likely receives only 20 to 30% of the energy per unit area that Earth receives. Less energy means, all else equal, less potential for biomass production. Infrared dominant spectrum. Red dwarfs emit most of their energy in the infrared, rather than visible light. On Earth, photosynthesis uses primarily red and blue light, with green light poorly absorbed, which is why plants appear green. K2-18b's organisms would need photosynthesis adapted to infrared wavelengths. Is this a deal breaker? Not at all. Earth has organisms that photosynthesize using infrared light. Some bacteria use bacteriochlorophyll, which absorbs in the near-infrared. Deep ocean algae photosynthesize using the blue-green light that penetrates deep water, showing that photosynthesis can adapt to different wavelengths. Life on K2-18b could evolve infrared-optimized photosynthesis. Moreover, K2-18b has alternative energy sources. Chemical energy from hydrothermal systems. K2-18b's ocean floor might have extensive hydrothermal vent systems, where superheated water rich in chemicals emerges from the interior. On Earth, hydrothermal vents host complex ecosystems completely independent of sunlight. Giant tube worms, specialized crabs, and unique bacteria thrive on chemical energy from the vents. K2-18b could have countless such vents spread across its enormous ocean floor, providing distributed energy sources that supplement or even rival photosynthesis. Thermal gradients. The temperature difference between K2-18b's warm surface waters and cold deep ocean could provide energy that thermosynthetic organisms exploit. While speculative, some researchers have proposed that life could theoretically harvest energy from temperature gradients through specialized molecular machinery. Tidal energy. K2-18b experiences strong tidal forces from its star. These tides, moving through the deep ocean, dissipate energy as heat and create current systems. While organisms can't directly harvest tidal energy, the mixing and currents tides create could enhance nutrient distribution and chemical cycling, indirectly supporting more productive ecosystems. Verdict. Earth's stronger, more photosynthesis-friendly sunlight gives it an edge in available energy. However, K2-18b's alternative energy sources might partially compensate. This category is closer than it initially appears, and Earth's advantage might be only 20 to 30% in terms of total energy available for biology. Water availability. K2-18b dominates life as we know it requires water. Every organism on Earth, from bacteria to blue whales, needs water for its biochemistry. Water is the universal solvent, the medium where life's chemical reactions occur, and a structural component of cells. Earth has plenty of water, oceans covering 71% of the surface, with a total volume of about 1.386 billion cubic kilometers. This seems like an enormous amount, and by human standards, it is. But K2-18b is a water world in a completely different league. Total water volume. K2-18b's ocean is estimated to be 100 to 500 kilometers deep, covering the entire planetary surface. The planet's radius is 2.6 times Earth's, giving it a surface area 6.76 times larger than Earth's. If we conservatively estimate the ocean depth at 200 kilometers, the total volume is approximately 210 billion cubic kilometers, about 150 times more water than Earth possesses. Universal availability. On Earth, water distribution is profoundly uneven. Oceans are salty and cover 71% of the surface. Fresh water is scarce. Only 2.5% of Earth's water is fresh, and most of that is locked in ice caps and glaciers. Rivers and lakes represent a tiny fraction of total water. Land life must actively seek water, traveling to rivers, lakes, or waterholes. Droughts devastate ecosystems. Much of Earth's land surface is water-scarce desert or semi-arid, limiting where life can thrive. On K2-18b, water availability is literally unlimited. Every organism, everywhere on the planet, has constant access to water. There would be no droughts, no deserts, no water scarcity limiting biodiversity. The concept of drought wouldn't exist in the K2-18b biosphere's vocabulary. Diverse aquatic environments. Earth's oceans, while vast, are relatively homogeneous in their physical structure. A surface layer receiving sunlight, a thermocline where temperature drops rapidly with depth, and cold, dark, deep waters. K2-18b's ocean, being 50 to 100 times deeper, would have vastly more diverse depth zones, each with distinct temperature, pressure, and light characteristics. This would create countless ecological niches not present on Earth. Near the surface, sunlit waters receiving infrared starlight, supporting photosynthetic life analogous to Earth's phytoplankton and kelp forests. Temperature, moderate, perhaps 20 to 40 degrees Celsius. Intermediate depths, 1 to 50 kilometers. Dim twilight zones where residual light penetrates but photosynthesis becomes challenging. This zone would be enormous compared to Earth's twilight zone. Temperature, gradually decreasing with depth. Pressure, increasing but not yet crushing. Deep ocean, 50 to 100 kilometers. Complete darkness, cold temperatures, high but manageable pressure. Chemosynthetic ecosystems clustered around hydrothermal vents, perhaps bioluminescent organisms creating their own light. Abyssal depths, 100 plus kilometers. Extreme pressure, near freezing temperatures, pitch black. On Earth, the deepest trenches at 11 kilometers host specialized life. K2-18b might have ecosystems adapted to pressures 10 times greater, representing forms of life we can barely imagine. This vertical structure creates extraordinary opportunities for biodiversity. On Earth, aquatic biodiversity is highest in coral reefs and coastal zones, complex, three-dimensional habitats with many niches. K2-18b's entire ocean is essentially a three-dimensional habitat hundreds of kilometers tall, offering evolutionary opportunities on a scale that dwarfs Earth's oceans. Verdict: K2-18b's water availability is superior by orders of magnitude. This might be its single greatest advantage over Earth: unlimited water everywhere, creating the potential for life to occupy virtually every cubic meter of a planetary ocean that contains 150 times more water than all of Earth's oceans combined. Protection from extinction events. Complicated Earth has suffered at least 5 major mass extinctions, each killing 70 to 96% of species. Ordovician Silurian, 443 million years ago, 85% of species extinct. Late Devonian, 375 million years ago, 75% of species extinct. Permian Triassic, 252 million years ago. 96% of species extinct. The Great Dying. Triassic-Jurassic, 201 million years ago. 80% of species extinct. Cretaceous-Paleogene, 66 million years ago. 76% of species extinct, including non-avian dinosaurs. Causes varied. Asteroid impacts, KPG extinction, massive volcanic eruptions, Permian-Triassic, rapid climate changes, ocean anoxia events, and possibly nearby supernovae or gamma-ray bursts. K2-18b's defenses against these threats. Asteroid/comet impacts. K2-18b's thick atmosphere would vaporize most impactors before they reach the surface. Objects that do penetrate would hit a deep ocean, creating less catastrophic effects than land impacts. The Chicxulub asteroid that killed the dinosaurs released energy equivalent to billions of nuclear weapons when it hit shallow water and bedrock. On K2-18b, a similar impact would release its energy into a deep ocean, creating massive tsunamis but no global firestorms, no ejector blanket blocking sunlight, and less atmospheric dust. The deep ocean would also buffer the thermal effects. Volcanic eruptions. K2-18b has no land volcanoes and possibly no volcanism at all if the planet lacks plate tectonics. Even if underwater volcanism exists, submarine eruptions don't inject ash and sulfur into the stratosphere the way land volcanoes do. Earth's worst extinction events involve massive volcanic provinces like the Siberian Traps erupting millions of cubic kilometers of lava and releasing enormous amounts of CO2 and sulfur. K2-18b's architecture prevents such events. Climate runaway. Earth's relatively shallow oceans and thin atmosphere make our climate vulnerable to positive feedback loops, warming that causes more warming, or cooling that causes more cooling. K2-18b's massive ocean and thick atmosphere would dampen such feedbacks, making climate runaway extremely unlikely. Ocean anoxia. Several Earth mass extinctions involved oceans losing oxygen, suffocating marine life. This occurs when warm, stagnant oceans stop circulating, allowing deep waters to become anoxic. K2-18b's tidal forcing and temperature gradients should maintain circulation, preventing global anoxia. However, K2-18b faces one extinction threat Earth doesn't: stellar flares. Red dwarf stars, especially when young, produce violent flares, sudden eruptions releasing enormous energy. A superflare could strip away portions of the atmosphere, irradiate the surface ocean, and potentially sterilize the planet. However, K2-18 is billions of years old, past its violent youth. The thick atmosphere provides significant shielding. The deep ocean protects organisms at depth even during flares. Life could evolve to shelter during flares or repair radiation damage. Modern red dwarfs flare less frequently and less violently than young ones. K2-18 appears to be a mature red dwarf with moderate flare activity. Concerning, but not prohibitively so. Verdict: advantage K2-18b, but not overwhelmingly. The planet's inherent protection from most extinction causes outweighs the stellar flare risk, but the comparison is closer than other categories. K2-18b's life would face fewer extinction events, but the ones it faces could be more severe. Evolutionary time. K2-18b wins spectacularly. Earth formed 4.5 billion years ago. Life appeared relatively quickly. The oldest fossils are 3.5 to 3.8 billion years old, suggesting abiogenesis occurred within Earth's first billion years. Complex multicellular life emerged about 600 to 800 million years ago, the Cambrian explosion. Intelligence evolved in humans within the last few million years. Earth has perhaps 1 billion years of habitability remaining before the Sun's gradually increasing luminosity triggers a runaway greenhouse effect, boiling away the oceans and ending the biosphere. After that, Earth has another 4 billion years before the Sun expands into a red giant and likely engulfs the planet. Total habitable lifetime, approximately 5 to 6 billion years, of which we're 75 to 80% through. K2-18b's timeline is incomparably longer. K2-18, like all red dwarf stars, burns hydrogen so slowly it will remain on the main sequence for 1 to 10 trillion years, 100 to 1,000 times longer than Sun-like stars. Even conservative estimates give red dwarfs habitable zone lifetimes of 1 trillion years or more. If life began on K2-18b at a similar time to Earth, roughly 4 billion years ago, it has already had as much time to evolve as Earth life. But while Earth's biosphere is nearing its end, K2-18b's could continue for trillions of years into the future, potentially 200,000 times longer than Earth's remaining habitable lifetime. What could life become with that much time? Earth, evolution produced, 0 to 2 billion years, simple single-celled organisms, prokaryotes, 2 to 1 billion years ago, complex cells with nuclei, eukaryotes, 800 to 600 million years ago, simple multicellular life, 541 million years ago, Cambrian explosion, complex body plans, eyes, predation, 370 million years ago, life colonizes land, 66 million years ago, mammals diversify after dinosaur extinction, 2 to 3 million years ago, human ancestors appear, 200,000 years ago, anatomically modern humans, 10,000 years ago, agriculture and civilization, 300 years ago, scientific revolution and industrial technology. Present, space exploration, artificial intelligence, genetic engineering. That's approximately 4 billion years from simple cells to technological civilization. Now imagine giving evolution not just another 4 billion years, but another 4 trillion years, 1,000 times longer than Earth's entire history. The possibilities are staggering. Biochemical sophistication. Given trillions of years, evolution on K2-18b might develop molecular machinery far more efficient than Earth's DNA/RNA/protein system. Life might discover information storage systems more compact than DNA, catalysts more versatile than proteins, or energy generation systems more efficient than ATP. K2-18b's organisms might operate with cellular machinery that makes Earth's biochemistry look primitive by comparison. Extreme specialization. With vast timescales and countless ecological niches in a planet-wide ocean hundreds of kilometers deep, evolution could produce levels of specialization we can barely conceive. On Earth, we have organisms adapted to extraordinary environments, bacteria living in boiling acid, fish surviving crushing pressure, insects with exquisitely specialized behaviors. Multiply that specialization by the factor of available time and space on K2-18b, and you get ecosystems of almost incomprehensible complexity. Novel sensory systems. Earth life evolved eyes independently dozens of times, showing that certain solutions are discovered repeatedly. But we're limited by what's useful in Earth's environments. K2-18b might have organisms with sensory systems Earth never evolved, perhaps magnetoreception far more sophisticated than Earth's migratory birds, perhaps sensitivity to gravitational gradients, perhaps perception of quantum phenomena we can't imagine. Given enough time, evolution explores all possible niches: swarm intelligence and collective consciousness. Earth has examples of collective intelligence: ant colonies, beehives, even human civilization. But these emerged recently in evolutionary terms. Given trillions of years, could K2-18b evolve organisms with neural networks that span vast distances, communicating through bioluminescent signals, electromagnetic pulses, or chemical gradients? Could there be ocean-wide cognitive systems where individual organisms are neurons in a planetary intelligence? Intelligence and technology. This is the most speculative but fascinating possibility. Earth took 4 billion years to produce technological intelligence. K2-18b has potentially 1,000 times longer. Even if intelligence is extraordinarily rare, say, only a 1 in 1,000 chance of evolving in any 4 billion year period, K2-18b would have multiple chances to develop it. But there's a challenge. K2-18b has no land, which seems necessary for technology. You can't smelt metal underwater. You can't discover fire. The path from intelligence to technology seems to require land, air, and the ability to manipulate materials with heat and chemistry that requires an oxidizing atmosphere. Unless there are alternative paths we haven't considered. Perhaps K2-18b has floating land masses, rafts of buoyant material that provide platforms above the ocean. Perhaps volcanic islands occasionally emerge and persist for millions of years, giving evolution time to produce amphibious intelligent life that can exploit these temporary land masses. Perhaps intelligence evolves without technology, creating sophisticated civilizations based on biological manipulation, genetic engineering performed through directed evolution, or architectures built from living materials rather than stone and metal. Or perhaps intelligence on K2-18b takes forms we wouldn't recognize. Distributed consciousness across populations. Chemical communication networks of such sophistication they constitute a form of technology. Or evolutionary strategies so advanced they appear designed rather than selected. Verdict: K2-18b's advantage in evolutionary timescale is so overwhelming, it's almost unfair to compare. Earth is a middle-aged planet with about 1 billion years left before its biosphere ends. K2-18b is essentially immortal from a biological perspective. With trillions of years available for evolution to explore possibilities Earth will never have time to discover. This might be K2-18b's single most significant advantage. Time itself is on its side in a way that's true for no planet orbiting a sun-like star. Biodiversity. Potential: K2-18b's staggering advantage. Earth hosts extraordinary biodiversity. Scientists have catalogued about 1.2 million species, but estimates of total species range from 5 million to 10 million or more. Most of this biodiversity is concentrated in specific environments. Coral reefs. Covering less than 0.1% of the ocean floor, reefs host 25% of all marine species. Rainforests. Covering about 6% of Earth's land surface, tropical rainforests contain perhaps 50% of all terrestrial species. Deep-sea vents. These tiny oases in the dark abyss host unique ecosystems found nowhere else. The pattern is clear. Biodiversity thrives where there's structural complexity, stable conditions, and abundant energy. Unfortunately, most of Earth's surface doesn't meet these criteria. Open ocean. The pelagic zone, open water away from coasts, is relatively barren, a blue desert with low nutrient and biomass density. Deserts. 33% of Earth's land is arid or semi-arid with low biodiversity. Polar regions. Ice-covered areas support limited life. Deep ocean floor. Cold, dark, food-poor abyssal plains host low-density, low-diversity communities. K2-18b's architecture creates the potential for biodiversity that makes Earth's look modest. Total habitable volume. Earth's oceans contain about 1.386 billion cubic kilometers of water, but most of this is relatively barren open ocean or nutrient-poor deep water. The productive zones, coastal areas, reefs, upwelling regions and hydrothermal vents represent perhaps 5 to 10% of the ocean's volume. K2-18b's ocean volume is approximately 210 billion cubic kilometers, 150 times more water than Earth. But the key difference is that a far higher percentage is potentially productive habitable space. No equivalent to Earth's deserts. The entire planet is habitable. Vertical stratification creating countless distinct depth zones, each a unique habitat. Planet-wide hydrothermal systems distributed across the ocean floor. Tidal mixing and circulation distributing nutrients efficiently. Stable conditions allowing extreme specialization. If even 30% of K2-18b's ocean is productive habitat, a conservative estimate given the better nutrient distribution, that's 63 billion cubic kilometers of productive habitat, about 150 times more than Earth's most productive zones. Ecological niches. Biodiversity is ultimately limited by the number of distinct ecological niches, unique combinations of environment, energy source, and evolutionary opportunity. Earth's most diverse ecosystems have the most niches. Coral reefs have three-dimensional structure with countless microhabitats. Tropical rainforests have vertical stratification from forest floor to canopy. K2-18b's ocean is essentially a three-dimensional habitat, hundreds of kilometers tall, with environmental gradients in pressure, from near zero at the surface to crushing pressures at depth. Temperature, from warm surface waters to near freezing depths. Light, from infrared-lit surfaces to pitch-black abyss. Chemistry, varying oxygen, nutrient, salinity, and pH gradients. Current systems, from strong surface currents to still, deep water. Energy sources: photosynthesis near surface, chemosynthesis at vents, perhaps exotic metabolisms in between. Each combination of these factors creates a distinct niche. The permutations are astronomical. While Earth might have millions of distinct ecological niches, K2-18b could have billions or trillions. Island biogeography principle. On Earth, biodiversity follows island biogeography principles. Larger areas support more species. The relationship isn't linear. Doubling area doesn't double species count, but it does increase it substantially. Studies show that for every tenfold increase in area, species richness increases by roughly 2 to 4 times. K2-18b has 6.76 times Earth's surface area and potentially 150 times the productive habitat volume. Even using conservative scaling relationships, this suggests K2-18b could support 10 to 50 times more species than Earth at comparable evolutionary stages. But there's more. Biodiversity is also time-dependent. Earth's biodiversity today is the result of 4 billion years of evolution, with periodic mass extinctions resetting the count. K2-18b's greater climate stability means fewer extinction events, allowing biodiversity to accumulate more steadily. And with trillions of years available, the cumulative species count could be orders of magnitude higher. Speciation rates. Speciation, the formation of new species, occurs when populations become isolated and diverge evolutionarily. On Earth, geographic isolation is the primary driver. Populations separated by mountains, water barriers, or distance evolve independently. K2-18b's planet-wide ocean might seem to prevent isolation, but actually creates different forms of it. Depth isolation. Populations adapted to different depths can't interbreed due to physiological constraints. A species evolved for surface pressure can't survive at 100-kilometer depth and vice versa. Current systems. Ocean currents create barriers to dispersal. Earth's oceans have distinct circulation gyres that partially isolate populations. Vertical stratification. Temperature, chemistry, and light gradients create sharp boundaries where surface species can't survive below and deep species can't survive above. Temporal isolation. Given enormous timescales, even slow geographic drift or climate variations could isolate populations long enough for speciation. The result? K2-18b's conditions favor rapid speciation, coupled with low extinction rates, a recipe for extraordinary biodiversity. Verdict: K2-18b's biodiversity potential is staggering, potentially 10 to 100 times Earth species count at comparable evolutionary stages, with the possibility of orders of magnitude more given sufficient time. This isn't just quantitatively different, it's qualitatively different. We're talking about a biosphere so complex that Earth's entire tree of life might represent just one small branch of K2-18b's evolutionary possibilities. Before we conclude that K2-18b is definitively superior to Earth, we need to rigorously examine the arguments for why it might not be as habitable as it appears. The stellar flare problem, more serious than previously thought. Recent research on red dwarf flares has revealed they're more dangerous than early models suggested. Dr. Ofer Cohen at the University of Massachusetts Lowell and his team studied how stellar flares affect exoplanet atmospheres around red dwarfs. Their findings are sobering. Even mature red dwarfs like K2-18 can produce superflares, events releasing 100 to 1,000 times more energy than the largest solar flares. A superflare striking K2-18b could strip atmospheric layers. The intense UV radiation and charged particles could photoionize and blow away portions of the upper atmosphere. Over millions of years, repeated flares might erode the atmosphere significantly. Generate harmful radiation. X-rays and UV radiation from flares would penetrate deep into the atmosphere, potentially reaching the ocean surface. This radiation would break apart complex molecules and could be directly lethal to surface-dwelling organisms. Create atmospheric chemistry chaos. Flares drive intense photochemistry, potentially producing toxic compounds or destroying protective molecules like ozone, if K2-18b has any. However, K2-18b has defenses. The thick hydrogen atmosphere is massive, perhaps 100 times more mass than Earth's atmosphere. Losing even 10% of it to stellar wind stripping over billions of years would still leave an atmosphere far thicker than Earth's. The atmosphere's sheer depth means that harmful radiation is absorbed in the upper layers, protecting the surface. Earth's ozone layer, just a few millimeters thick if compressed, protects us from UV. K2-18b's atmosphere is hundreds of kilometers thick. Life could adapt. On Earth, organisms have evolved multiple mechanisms for radiation resistance. DNA repair enzymes that fix radiation damage, radioprotective compounds that shield cells, behavioral adaptations like hiding during peak radiation, extremophile bacteria that survive radiation doses thousands of times higher than would kill humans. K2-18b's life would evolve under higher background radiation than Earth life. Natural selection would favor radiation-resistant organisms. After billions of years, K2-18b's biosphere might be naturally resistant to radiation levels that would devastate Earth life. Still, this remains K2-18b's most significant vulnerability. If K2-18 is an unusually active red dwarf, frequent superflares could make surface habitability challenging or impossible. The tidal locking dilemma. K2-18b likely became tidally locked to its star within the first billion years of its existence. This means one hemisphere permanently faces the star, eternal day, while the other faces away, eternal night. The day side would be hot, the night side freezing. The transition zone between them, the terminator, experiences eternal twilight. On first consideration, this seems catastrophic for habitability, but the reality is more nuanced. Atmospheric circulation moderates extremes. K2-18b's thick atmosphere would transport heat from day to night side through powerful winds. Computer models by Dr. Jeremy Leconte at the University of Bordeaux show that tidally locked Hycean worlds with thick atmospheres maintain habitable conditions across much of their surface, including the night side. The day-night temperature difference drives atmospheric circulation. Heated air on the day side rises, flows toward the night side at high altitude, cools and sinks on the night side, then flows back to the day side at low altitude. This creates a planet-scale convection cell that efficiently transports heat. Ocean circulation amplifies heat transport. The global ocean adds another heat transport mechanism. Warm surface water from the day side flows toward the night side, while cold, deep water flows from night to day. The ocean's enormous heat capacity means it can store heat from the day side and release it on the night side, moderating temperature extremes. The terminator zone. Even if day and night sides are challenging for life, the terminator, the boundary between them, would be a permanent band of twilight conditions circling the planet. This zone might be optimal. Moderate temperatures, perpetual dim light, and protection from the star's most intense radiation. Life on K2-18b might concentrate in this twilight zone, creating a ring of biodiversity around the planet's circumference. This isn't necessarily a disadvantage. It might create unique selective pressures that drive interesting evolutionary innovations. Verdict: tidal locking presents challenges but likely not deal breakers. The thick atmosphere and ocean should maintain habitable conditions across most of the planet, and the terminator zone might be uniquely hospitable. The high-pressure challenge. K2-18b's surface gravity is approximately 2.6 times Earth's. For a human standing on a solid surface, if one existed, everything would feel 2.6 times heavier. Combined with the thick atmosphere, surface pressure could be 100 to 1,000 times Earth's sea level pressure. For comparison, the deepest points in Earth's oceans experience about 1,100 times atmospheric pressure. Life exists there, specialized fish, crustaceans, and microbes, but it's adapted specifically for high pressure. Bring a deep-sea fish to the surface and it dies. Swim bladders expand. Dissolved gases come out of solution. Cellular processes fail. K2-18b's surface-dwelling life would face similar challenges. Every organism would need to maintain cellular integrity under crushing pressure. This requires pressure-adapted proteins whose shape and function are optimized for high pressure. Specialized cell membranes that remain fluid despite compression. Pressure-compatible biochemistry, where reaction rates and equilibrium points are appropriate for the environment. Earth's deep-sea life proves this is possible, but it raises a question. Could complex, large organisms evolve under such conditions? On Earth, the largest deep-sea organisms are relatively small compared to shallow water or land creatures. The biggest deep-sea fish are perhaps 2 to 3 meters long, far smaller than surface-dwelling whale sharks, 12+ meters, or blue whales, 30 meters. The largest land animal ever, Argentinosaurus, was perhaps 30 meters long and 70 tons. Size correlates with energy availability and structural constraints. High pressure affects both. Structural challenges. Supporting a large body is harder under high pressure and strong gravity. Bones or shells need to be stronger, which requires more energy to build and maintain. Energy metabolism. High pressure affects enzyme kinetics and cellular metabolism. It's energetically expensive to maintain cellular functions under extreme pressure. K2-18b's life might be constrained to smaller sizes than Earth's largest organisms. Instead of blue whales, imagine whale equivalents the size of dolphins. Instead of giant squids, think squid analogues the size of herrings. But smaller doesn't mean less sophisticated. Intelligence isn't strictly correlated with body size. Crows and parrots are highly intelligent despite being small, and octopi have complex behavior despite their modest size. K2-18b could host sophisticated ecosystems of small, pressure-adapted organisms. Verdict: high pressure is a constraint but not prohibitive. Life would be different from Earth's surface life, smaller, more pressure-adapted, and biochemically specialized. But different doesn't mean worse in any objective sense. The oxygen-free atmosphere problem. K2-18b's hydrogen-rich atmosphere contains little to no free oxygen. This has profound implications for the complexity of possible life. On Earth, free oxygen in the atmosphere was produced by photosynthetic cyanobacteria, starting about 2.4 billion years ago. This great oxygenation event was actually catastrophic for anaerobic life. Oxygen was toxic to early organisms, but it enabled the evolution of complex life. Why? Because aerobic respiration using oxygen is far more energetically efficient than anaerobic metabolism. Aerobic respiration. One glucose molecule yields about 32 ATP, the cell's energy currency. Anaerobic fermentation. One glucose molecule yields about 2 ATP. Aerobic metabolism is roughly 16 times more efficient. This efficiency enabled the evolution of complex, active, energy-intensive organisms, animals that move quickly, hunt, evade predators, and eventually think. K2-18b's hydrogen atmosphere means aerobic respiration as we know it is impossible. Life there would need alternative metabolisms. Methanogenesis, using hydrogen and CO2 to produce methane and energy. Earth has methanogenic archaea that do this, but they're relatively simple organisms. Sulfur metabolism, using sulfur compounds as electron acceptors instead of oxygen. Many Earth bacteria do this in oxygen-free environments. Hydrogen metabolism. Some bacteria metabolize hydrogen directly, but it's not very efficient. Alternative electron acceptors. Perhaps K2-18b's life uses novel chemistry we haven't considered, exotic molecules that serve the same role as oxygen in Earth biochemistry, but work in a hydrogen atmosphere. The question is, can any of these metabolisms power complex, active, intelligent life? The honest answer? We don't know. Earth's only example of technological intelligence, humans, evolved using oxygen-based metabolism. But that's a sample size of 1, which means we can't draw strong conclusions. It's possible that intelligence requires the energy density that only aerobic metabolism provides. If so, K2-18b might be limited to microbial life and simple multicellular organisms, a rich biosphere by microbial standards, but lacking the charismatic megafauna and intelligent life that make Earth's biosphere special to us. Alternatively, given trillions of years, evolution might discover metabolic pathways we can't imagine that provide sufficient energy for complexity without oxygen. K2-18b's life might be different from Earth's complex life, but not necessarily simpler or less sophisticated. Verdict: this is perhaps the strongest argument that K2-18b might not be better than Earth for hosting complex intelligent life. The oxygen constraint is real and might fundamentally limit biological complexity. However, Our Earth-centric bias might be blinding us to alternative possibilities. We have almost no information about K2-18b's ocean composition. Is it pure water? Unlikely. Planets accumulate salts and minerals. Salt water like Earth's oceans? Possible, if the planet has similar geological processes. Exotic brines? Perhaps rich in ammonia, methanol, or other compounds that wouldn't exist in Earth's oceans. Acidic or alkaline? pH could be anywhere from battery acid to drain cleaner. Ocean chemistry matters enormously for biology. Earth's life is specifically adapted to specific salinity, about 3.5% salt in seawater. Neutral to slightly alkaline pH. Ocean pH is about 8.1. Specific mineral content: sodium, chloride, magnesium, calcium, sulfate. Different ocean chemistry would require different biochemistry. This isn't necessarily a problem. Life is adaptable, but it's an unknown that could work for or against habitability. If K2-18b's ocean is extremely acidic, alkaline, or has toxic dissolved metals at high concentration, it might be hostile to complex life. Conversely, if the chemistry happens to be even more conducive to life than Earth's oceans, perhaps with better nutrient availability or more optimal pH, it could be an advantage. We simply don't know yet. Future observations might allow us to infer ocean chemistry from atmospheric composition. Certain atmospheric gases would indicate specific ocean chemistries, but for now, this remains a significant unknown. Verdict: unknown. This could work for or against K2-18b's habitability. Until we have better data, it remains a major uncertainty in assessing the planet's suitability for life. What life on K2-18b might actually look like. A detailed speculation. If life exists on K2-18b, and especially if it's had billions of years to evolve, what would it be like? Let's paint a detailed picture based on the planet's characteristics. Microbial foundation, the deep biosphere. At the base of K2-18b's ecological pyramid would be microorganisms, bacteria and archaea analogues filling countless niches. Surface photosynthesizers, floating or swimming in the top few meters of ocean, these organisms would photosynthesize using K2-18's infrared light. They might be red, dark brown or black to maximize absorption of infrared wavelengths. Vast blooms of these photosynthesizers could cover millions of square kilometers, visible from space as dark patches on the ocean, including, possibly, producing the dimethyl sulfide we've detected. Chemosynthesizers. Clustered around hydrothermal vents across K2-18b's ocean floor, these organisms would derive energy from chemical gradients, hydrogen sulfide, methane, hydrogen gas, or exotic chemistries. They'd form the base of entire ecosystems independent of starlight, analogous to Earth's hydrothermal vent communities, but vastly more extensive given the enormous ocean floor area. Depth specialists. Throughout the water column, specialized microbes would occupy niches defined by specific combinations of pressure, temperature, chemistry, and light. Some might metabolize dissolved hydrogen from the atmosphere. Others might feed on organic matter raining down from upper layers. Still others might engage in symbiotic relationships with larger organisms. Biofilm architects. On any solid surfaces, vent structures, mineral precipitates, or even on larger organisms, biofilms would form complex three-dimensional structures. These microbial cities would have specialized zones, outer layers doing photosynthesis or chemosynthesis, middle layers processing nutrients, inner layers engaged in communication or genetic exchange. Simple multicellular life, building complexity. Given billions of years, K2-18b's life would likely progress from single cells to multicellular organisms, just as Earth life did. But the forms might be distinctly alien. Colonial organisms. Imagine vast floating mats of cells, kilometers across, forming at the ocean surface. Individual cells specialize. Some photosynthesize, others maintain buoyancy structures, still others defend against predators or reproduce. The colony acts as a single organism, despite being millions of cells. Earth has examples, Portuguese man-o'-war, some algae, but K2-18b could have this strategy at vastly larger scales. Pressure-adapted forms. Soft-bodied organisms dominate, as hard shells are energetically expensive at high pressure. Think jellyfish, octopi, hagfish, gelatinous, flexible, able to maintain cellular integrity despite crushing pressure. K2-18b's fish might be entirely boneless, with cartilaginous structures at most, bodies designed to flex and compress. Bioluminescence everywhere. In the dim, infrared-lit waters and especially at depth, organisms would produce their own light for communication, complex flashing patterns for mating, territorial displays, or coordinating group behavior. Hunting, lures to attract prey, like Earth's anglerfish, but more sophisticated. Defense, startling predators with sudden flashes or creating bioluminescent decoys. Camouflage, counter-illumination to match background light, making the organism invisible to predators below. K2-18b's depths might be a wonderland of bioluminescence, creatures producing blues, greens, reds, and colors we can't perceive, creating light shows of staggering complexity. Filter feeders. Given the likely abundance of microbial life, filter feeders would be common. Organisms with enormous surface area for filtering, think of baleen whales but perhaps even larger given the ocean's size, would strain microorganisms from the water. These might be the planet's largest organisms, drifting slowly through nutrient-rich waters. Complex life, the apex of K2-18b evolution. With billions of years and stable conditions, K2-18b could evolve complex organisms we can barely imagine. Sensory sophistication. Electroreception. Many Earth organisms, sharks, platypuses, sense electrical fields. On K2-18b, this might be far more developed, organisms mapping their surroundings through electrical sensing, communicating through electrical pulses, or even stunning prey, with electric discharges far more powerful than Earth's electric eels. Magnetoreception, sensing the planet's magnetic field for navigation. Given K2-18b's size, its magnetic field might be strong, providing detailed navigational information. Chemical sensing, smell, and taste might be extraordinarily acute, allowing organisms to detect prey, predators, or mates from great distances through chemical gradients in the water. Pressure sensing, detecting minute pressure changes to sense movement, locate prey, or navigate. Earth's fish have lateral lines for this. K2-18b's organisms might have entire body surfaces covered with pressure sensors of exquisite sensitivity. Infrared vision, eyes adapted to see in the infrared wavelengths of K2-18's light, possibly with sensitivity extending into wavelengths we can't perceive. Behavioral complexity. Tool use. Even without hands, some organisms might use tools. Octopi on Earth use coconut shells as portable shelters. K2-18b might have organisms that manipulate objects, perhaps volcanic rocks as hammers to break open shells, or organic tools they cultivate from symbiotic organisms. Social structures. Complex societies analogous to Earth's dolphins, elephants, or primates. Given enough time, social complexity could rival or exceed anything on Earth. Elaborate hierarchies, culture transmitted across generations, cooperative hunting or building strategies. Migration. Vast seasonal or life cycle migrations, perhaps from surface to depth, or following current systems around the planet. Some species might spend years or decades in transit, analogous to sea turtles or salmon, but on planetary scales. Symbiosis everywhere. Many K2-18b organisms might not be individuals but symbiotic partnerships. Organisms with photosynthetic symbionts, like Earth's corals with zooxanthellae, providing energy. Partnerships between species with complementary abilities, one providing locomotion, the other providing sensing or feeding. Multi-species clusters that function as single entities, with specialized members handling different tasks. Could intelligence evolve on K2-18b? This is the most speculative and fascinating question. The path to intelligence on Earth involved complex brains, energy expensive, social interaction, language, cooperation, manipulation, hands, tool use, environmental challenges, variable conditions favoring innovation. K2-18b has challenges. No oxygen means less metabolic energy for energy-expensive brains. No land means no clear path to tool use or fire. Stable conditions might reduce selective pressure for innovation, but it also has opportunities. Trillions of years mean even improbable paths have many chances to occur. Enormous ocean provides countless niches and opportunities for complexity. Social complexity could evolve in ocean settings. Earth dolphins, whales and octopi show intelligence without land or fire. One speculative scenario: distributed intelligence. What if K218b evolves intelligence not in individuals but in collectives? Imagine schools of thousands of individuals with specialized roles. Communication through bioluminescence, electrical pulses, or chemical signals. Information processing distributed across the group. Individual organisms are like neurons. The school is the brain. The collective exhibits problem-solving, learning, and possibly self-awareness. This swarm intelligence might not be technological, no spaceships or radio telescopes, but could be sophisticated enough to constitute true intelligence. The collective might even modify its environment biologically, cultivating certain microorganisms, engineering currents through coordinated movement, or creating structures from living materials. After trillions of years, could such intelligence become something we'd recognize as technological? Perhaps, if the collectives discover ways to manipulate materials chemically or biologically, they might create a form of biotechnology, not machines, but living tools engineered through selective breeding or directed evolution. It's wild speculation, but given unlimited time and a stable environment, evolution explores every possibility. Intelligence might be inevitable given enough time, even in environments that seem hostile to it. The DMS detection, while exciting, is just the beginning of unraveling K218b's mysteries. Over the next few decades, a cascade of new observations and technologies will either confirm K218b's habitability and possible biology, or reveal we've misinterpreted the data. Short term, 2025 to 2027, confirmation phase. James Webb will observe K2-18b multiple additional times. Each observation provides more atmospheric data. Seasonal variations. Does the DMS concentration change with K2-18b's orbital position? Seasonal variations would suggest biology responding to changing light levels. Other biosignatures. Are there other gases associated with life? Methyl chloride, carbonyl sulfide, and other organosulfur compounds might accompany DMS if produced biologically. Atmospheric layers. Can we detect vertical structure in the atmosphere? Different altitudes might show different chemistries, revealing atmospheric dynamics and chemistry. Ground-based telescopes will also contribute. The Extremely Large Telescope, ELT, in Chile, set for first light in 2028, will have a 39-meter mirror, the largest optical telescope ever built. While ground-based telescopes struggle with Earth's atmospheric interference, advanced adaptive optics systems can partly compensate. ELT might detect atmospheric features Webb misses, or provide complementary data. By 2027, we should know with high confidence whether the DMS detection is real and whether it's seasonal or variable. We'll have a much better atmospheric characterization, pressures, temperatures, wind patterns, and the full inventory of gases present. Medium term, 2028 to 2035, characterization phase. NASA is planning the Habitable Worlds Observatory, HWO, a space telescope specifically designed to directly image and characterize Earth-like exoplanets. While optimized for rocky planets, HWO could provide extraordinary data on K2-18b. Direct imaging. Actually seeing K2-18b as a pixel or small disk, not just detecting its effect on starlight. Day-night differences. If tidally locked, direct imaging could distinguish the day side from night side, revealing temperature and atmospheric differences. Weather patterns. Long-term monitoring might detect clouds, storms, or other atmospheric dynamics. Surface properties. While we wouldn't see surface details, we might detect the signature of ocean versus possible land masses or floating structures. The European Space Agency's Plato mission, launching 2026, and Ariel mission, launching 2029, will also study exoplanet atmospheres. Ariel specifically targets atmospheric chemistry and will observe numerous sub-Neptunes, including K2-18b. By 2035, we'll have comprehensive data on K2-18b's atmosphere, climate, and potentially even surface conditions. If biosignatures are present, we'll have multiple independent confirmations from different instruments and techniques. Long-term, 2040 to 2050, advanced characterization. Future technologies might enable observations that seem impossible today. Optical interferometry, linking multiple space telescopes together to create a virtual telescope with enormous effective diameter. This technique, already used for radio astronomy, could be extended to optical wavelengths with space-based platforms. An optical interferometer with baseline distances of thousands of kilometers could potentially resolve K2-18b's disk into multiple pixels, detect large-scale surface features, map atmospheric circulation patterns, perhaps even detect city lights or industrial pollution if an advanced civilization exists there. Technosignatures. If intelligent life exists on K2-18b and uses technology, we might detect industrial chemicals, chlorofluorocarbons, nitrogen dioxide, or other pollutants in the atmosphere. Artificial light. Illumination on the night side that doesn't match natural bioluminescence. Megastructures. Large artificial structures that affect the planet's light curve during transits. Radio signals. Though this seems unlikely for an ocean world without electronics, some exotic technologies might produce detectable signals. Sample return. This is purely speculative and probably not achievable within this century, but we can imagine. A probe sent to K2-18b that scoops atmospheric samples and returns them to Earth. The journey would take centuries with current propulsion, but future technologies, fusion drives, antimatter propulsion, or even generation ships might make it feasible. Actually analysing K2-18b's atmosphere in Earth laboratories would definitively answer questions about biology, chemistry, and composition. Beyond the scientific excitement, K2-18b forces us to confront profound philosophical questions about our place in the universe and the nature of life itself. The end of Earth-centrism. For most of human history, we believed Earth was the centre of the universe. Copernicus and Galileo demolished that geocentric view, showing that Earth orbits the Sun. Then we discovered our Sun is one ordinary star among hundreds of billions in our galaxy. Then we found our galaxy is one among hundreds of billions in the observable universe. Each revelation made us smaller, less central, less special. K2-18b might represent the next step in this philosophical journey, the recognition that Earth isn't even the ideal template for life. We've been searching for Earth 2.0, assuming our planet represents the pinnacle of habitability. K2-18b suggests that assumption is wrong. Hycean worlds might be better platforms for life than Earth-like planets. They're more common. Sub-Neptunes are the most common planet type we've found, and red dwarfs are the most common stars. They're more stable. Massive oceans buffer climate changes. They're longer-lived. Red dwarf stars shine for trillions of years. They might support more biodiversity. Planet-spanning oceans provide enormous habitat volume. If K2-18b truly hosts life, especially if that life is more diverse, more sophisticated, or more ancient than Earth's, then we must accept that Earth is not the cosmos's masterpiece. We're not living on the best of all possible worlds. We're living on the world we happened to evolve on, which happens to be good enough, but not necessarily optimal. This realization is both humbling and liberating. Humbling because it further diminishes human specialness. Liberating because it expands the possibilities for life in the universe. If Hycean worlds can host life, and if they're common, then the universe might be far more alive than we dared hope. The Fermi paradox, where is everybody, becomes even more puzzling if Hycean worlds are commonly inhabited. The classic paradox goes like this. Our galaxy is 13 billion years old and contains hundreds of billions of stars. Even if intelligent life is rare, and even if most don't develop technology, and even if most technological civilizations don't attempt interstellar colonization, we'd still expect someone to have colonized the galaxy by now. Space is vast, but so is time. Given 13 billion years, even slow expansion should fill the galaxy. Yet we see no evidence of alien civilizations, no megastructures, no radio signals, no von Neumann probes visiting every star system. The galaxy appears lifeless, except for us. K2-18b makes this even more puzzling. If Hycean worlds are common, they appear to be. They're better for life than Earth-like worlds, they might be. The galaxy contains billions of such worlds, probably true. Many have been habitable for billions of years longer than Earth. Red dwarfs are ancient. Then where are all the civilizations that should have evolved on these worlds? Several possibilities, none entirely satisfying. The ocean prison hypothesis. Perhaps Hycean worlds are common and teeming with life, but that life never becomes technological because ocean-dwelling organisms can't develop technology. No fire, no metallurgy, no electronics, just biological sophistication without the ability to build radio telescopes or spaceships. The galaxy could be filled with intelligent ocean dwellers who will never join the cosmic conversation because their environment prevents technological development. The intelligence filter. Maybe intelligence is far rarer than we think. Earth took 4 billion years to produce technological intelligence, and it might be a 1 in a trillion fluke. Even giving K2-18b trillions of years doesn't guarantee intelligence evolves. Perhaps the step from complex life to intelligent life is so improbable that most biospheres, however diverse, never make that leap. The self-destruction filter. Perhaps civilizations commonly arise but destroy themselves before achieving interstellar capability. Nuclear war, ecological collapse, AI disaster, engineered pandemics. Technological civilizations might have a short lifespan. K2-18b might have evolved intelligence multiple times over its long history, and those intelligences might have destroyed themselves before we evolved. The transcendence hypothesis. Maybe advanced civilizations transcend physical existence, uploading consciousness into computers, leaving the physical universe for higher dimensions, or otherwise moving beyond the need for planets and resources. They become invisible to our telescopes and radio receivers because they're no longer doing anything we'd recognize as civilization. They're hiding. Perhaps there are protocols among galactic civilizations not to interfere with primitive species like us. Star Trek's Prime Directive might be standard practice, with K2-18b's hypothetical civilization, and countless others, watching us silently until we reach some threshold of maturity or capability. We're early. Despite the universe's age, perhaps we're among the first technological civilizations. Life might require multiple generations of stars to produce heavy elements. Complex life might require specific conditions that only recently became common. We might be pioneers, with most of the galaxy's eventual civilizations still in their microbial or simple multicellular stages. None of these explanations is entirely satisfying, which makes the Fermi paradox so compelling. K2-18b, if inhabited, sharpens the paradox. We've potentially found a living world, but still no evidence of technological civilization anywhere. The ethics of contact. If K2-18b definitively proves to host life, even microbial life, humanity will face unprecedented ethical questions. Should we try to contact them? At 124 light-years away, radio signals would take 124 years to reach K2-18b, with another 124 years for a reply. A 248-year conversation delay. Any message we send won't be answered in our lifetimes, or our children's lifetimes, or our great-great-grandchildren's lifetimes. But the question isn't just about practicality. It's about whether we have the right to announce our presence to another biosphere. Some argue yes. Scientific duty. If we can communicate, we should. The potential for exchanging knowledge justifies the attempt. Cosmic loneliness. Making contact, even across centuries, connects humanity to something larger than ourselves. Inevitability. If we can detect them, they can eventually detect us. Contact is inevitable. We might as well initiate it. Others argue no. Prime Directive. We shouldn't interfere with other biospheres or civilizations, especially less advanced ones. Contact could be disruptive or harmful. Unknown risks. We don't know how K2-18b's life or civilization, if it exists, would react to contact. We might trigger panic, religious crises, or other unforeseen consequences. We're not ready. Humanity can't agree on basic planetary issues. How can we presume to speak for Earth to another world? And there's a darker consideration. Should we advertise our location? Some scientists, including Stephen Hawking before his death, warned that announcing our presence might attract hostile attention. If the galaxy contains aggressive expansionist civilizations, broadcasting "Here we are" could invite invasion or destruction. This seems paranoid. Surely any civilization capable of interstellar travel has long since detected Earth's biosignature or radio leakage. But it's a risk some take seriously enough to advocate silence. Listen, but don't transmit. Study, but don't reveal ourselves. K2-18b forces these questions from abstract philosophy into practical policy. If microbial life is confirmed, do we send messages to the microbes? Probably not. There's no one to receive them. But if biosignatures suggest complex life, or if we detect technosignatures suggesting intelligence, then we face a genuine decision about contact. International protocols don't currently exist for this scenario. The decision of whether to contact K2-18b would probably be made by whoever has the biggest radio telescope and the strongest political will, not through coordinated global consensus. That's both exciting and terrifying. Redefining habitable. K2-18b is teaching us that our definition of habitable has been too narrow. For decades, we defined habitable as Earth-like, rocky composition, Earth-like size and mass, Earth-like distance from a Sun-like star, nitrogen-oxygen atmosphere, liquid water on surface. K2-18b meets only one criterion, liquid water, yet it appears to be habitable, potentially even superior to Earth in key ways. This should revolutionize how we search for life. Expand target list. Include subneptunes, not just rocky planets. Include red dwarf systems, not just Sun-like stars. Include tidally locked worlds, not just planets with day-night cycles. New biosignatures. Look beyond oxygen and ozone. Search for DMS, methyl chloride, phosphine, and other molecules that might indicate life in non-Earth chemistries. Rethink requirements. We don't need plate tectonics. We don't need a large moon to stabilize rotation. We don't need continents. We don't even need an oxygen atmosphere. Life is more flexible than our imaginations. This expansion is profound. Under old assumptions, the galaxy might have tens of millions of habitable worlds. Under new assumptions, accounting for Hycean worlds, there might be billions. The difference between those numbers is the difference between cosmic loneliness and a universe teeming with life. Dr. Lisa Kaltenegger at Cornell, who directs the Carl Sagan Institute, summarized the paradigm shift. K2-18b is showing us that we've been looking for ourselves when we should have been looking for life. Those aren't the same thing. Life is creative, adaptable, opportunistic. It finds ways to exist that we wouldn't design if we were creating habitable planets from scratch. K2-18b might be weird by our standards, but weird doesn't mean inhospitable. It means different, and different might be the universe's preferred solution. Let's imagine it's 2027. James Webb has observed K2-18b6 more times. The DMS signal strengthens with each observation and shows seasonal variation. Additional organic molecules are detected. The atmospheric chemistry defies all non-biological explanations. The scientific consensus solidifies. K2-18b hosts life. How would this change humanity? Scientific revolution. Every biology textbook would need revision. Astrobiology would transform from a speculative field to an empirical science with actual alien life to study. Questions that were philosophical would become testable. Is life's origin chemistry specific, or can it use different elements? Is DNA/RNA universal, or do other information storage systems exist? Are cells universal, or can life be organized differently? Is evolution by natural selection universal, or are there alternatives? Funding for space telescopes and exoplanet research would skyrocket. Nations would compete to build more powerful observatories. Private companies would invest in technologies to study or eventually reach K2-18b. The Nobel Prize in Physics, chemistry, and physiology/medicine would probably all go to researchers involved in the K2-18b discovery and characterization for decades to come. Philosophical and religious impact. Every religion and philosophical tradition would grapple with the implications. Christianity. Does K2-18b's life have original sin? Did Jesus' sacrifice apply to them? Are they saved, or do they need their own Messiah? Christian theologians have debated extraterrestrial life for centuries with no consensus. Confirmation would force the debate from abstract to urgent. Islam. The Quran mentions that Allah created life on other worlds. Islamic scholars might see K2-18b as confirmation of Scripture, though questions would arise about whether K2-18b's life has souls and what their afterlife status might be. Buddhism and Hinduism. These traditions generally have less difficulty accommodating alien life, as both accept vast cosmos with countless worlds and life forms. K2-18b might be seen as confirmation of ancient wisdom about cosmic diversity. Secular humanism. The impact might be most profound here. If humanity isn't unique, if intelligence can arise on worlds radically different from Earth, then human specialness becomes harder to justify. Ethical frameworks based on human uniqueness would need revision. Science fiction would explode with K2-18b-inspired stories. Films, novels, games, and art would explore what K2-18b's life might be like. The planet would become a cultural touchstone, like Mars has been, but more so because it's real and inhabited. Music, poetry, and visual art would process humanity's expanded cosmic context. Just as the Apollo moon landings inspired a generation of artists, K2-18b's confirmation as a living world would inspire new forms of expression, grappling with our place among inhabited worlds. Education would change. Children would grow up knowing that life exists elsewhere. This might make them more cosmopolitan, more comfortable with diversity, more capable of thinking beyond human-centric frameworks. Or it might create existential anxiety as they grapple with our cosmic insignificance. Political and economic impact. Space agencies' budgets would likely increase dramatically. Politicians who previously saw space as a luxury would recognize it as frontier science with profound implications. International cooperation and competition in space would intensify. But there might also be social disruption. Some people would handle the news well. Cool, aliens exist. Others might experience existential crises, religious doubts, or fear. Conspiracy theories would flourish. Governments have known about K2-18b life for years. They're hiding the truth about alien technology. K2-18b is preparing to invade. The stock market might fluctuate. Space-related companies would see their valuations soar. Tourism companies might promote stargazing packages to view K2-18b through telescopes. The discovery would ripple through economy and society in unpredictable ways. Over decades and centuries, confirmed life on K2-18b would fundamentally reshape human civilization's self-understanding. We'd be forced to accept that Earth is one living world among many, perhaps among billions, that our biosphere, while precious to us, isn't unique, that intelligence, if it exists on K2-18b, arose independently from completely different conditions and might take forms we don't recognize. This might make us more protective of Earth. If life is common but Earth is our only home, then preserving our planet becomes even more urgent. We can't move to K2-18b. It's forever beyond reach. We have only one habitable world that's accessible, and we need to protect it. Or it might make us more ambitious. Knowing life exists elsewhere might motivate the development of technologies for long-term space survival. If we can't go to K2-18b, perhaps we can reach other, closer habitable worlds. The discovery might catalyze humanity's transformation into a multiplanetary species, or perhaps, most profoundly, it would teach us humility and perspective. We'd see ourselves as one experiment in biology among countless others. Our particular form of intelligence, our specific chemistry, our individual history, would be recognized as one path among many. This might make us more curious, more open-minded, more willing to consider possibilities beyond our experience. Conclusion: K2-18b and the future of habitability science. The story of K2-18b is really the story of expanding human understanding. With each generation, we've broadened our conception of what's possible. Ancient humans, Earth is all that exists. Classical era, Earth is a sphere among celestial spheres. Copernican revolution, Earth orbits the Sun. Modern era, the Sun is one star among billions. Exoplanet era, planets are common around other stars. Now, habitable worlds are common, taking forms we never imagined. K218b represents the latest chapter in this expansion. It's teaching us that habitability is a bigger concept than we realized. It's not just Earth-like or nothing. It's a spectrum of possibilities, with multiple architectures that work under different conditions. Whether K218b truly hosts life remains uncertain as of this writing. The DMS detection is compelling but not yet definitive. The planet clearly occupies a habitable zone and has atmospheric conditions consistent with liquid water. Whether that potential has been realized, whether K218b's ocean is barren or teeming, is the question that will drive astronomy and astrobiology for the next decade. But regardless of whether life exists there now, K218b has already taught us something profound. Earth isn't the template for habitability. It's one example among many possible configurations. Hycean worlds might be more common than Earth-like planets. They might be more stable, they might last longer, they might support more biodiversity. In many measurable ways, they might be better for hosting life. But better is always contextual. K2-18b is better for K2-18b's life, whatever form that takes. Earth is better for Earth life, including us. We couldn't survive on K2-18b. The pressure would crush us, the atmosphere would suffocate us, the gravity would exhaust us. Yet recognizing that another world might be objectively superior for life in general, more stable, longer-lived, more diverse, should expand our cosmic perspective. We're not living on the universe's masterpiece. We're living on a habitable world that's good enough, and we should be grateful for its goodness while recognizing that the universe's creativity extends far beyond Earth's particular solution to habitability. K2-18b is a world of water under hydrogen skies, orbiting a red star that will shine for trillions of years. It might be sterile, it might host microbes, it might teem with complex life we can barely imagine, or it might be home to intelligence pondering the same questions we are, looking at the cosmos through eyes adapted to infrared starlight, wondering if they're alone. We don't know yet, but we're asking, and that's what makes us human. The drive to explore, to understand, to reach across the vast darkness and ask, what's out there? Are we alone? And what can we learn from worlds unlike our own? K2-18b is 124 light-years away, close enough to study, too far to touch. But studying it changes us. Learning about it expands our understanding of what's possible. And recognizing that it might be better than Earth in some ways teaches us the humility we need as we venture into a cosmos far more diverse than our ancestors imagined. The universe is vast. It contains wonders we're only beginning to glimpse. K2-18b might be one of them. A water world under alien skies. A planet that could be better than Earth for life. A place that challenges everything we thought we knew about habitable worlds. And it's just the beginning. There are billions of worlds out there, each potentially teaching us new lessons about life, habitability, and the cosmic possibilities that await discovery. The age of exploration isn't over. It's just expanding to scales our ancestors couldn't have dreamed of. If this discovery blew your mind and made you rethink everything you thought you knew about habitable worlds, then you need to hit that subscribe button right now. We're on the cutting edge of the most exciting era in space exploration, and I'll be bringing you every new revelation as scientists decode the mysteries of exoplanets like K2-18b. Drop a comment telling me what you think. Could K2-18b really host life? Or is there another explanation for what we're seeing? And smash that like button if you want more deep dives into the cosmic discoveries that are rewriting our understanding of the universe. The next video might reveal something even more shocking. See you there.